So I think there's a problem here on this equation. So this has an I here, okay? So this is a P CR pi squared ETI over L squared, the basis of which is your Euler equation here. Okay, so this has an I there. Okay, so this is now your double Angular equation. And the last one is the Shanley proposal, which resolved the apparent inconsistencies in the above theories. And today, the basic tangent modulus concept was the one that is accepted as the correct one for inelastic backlink. So what Shanley did is uh, he verified the work of Ankeser and found out that your PS, or the P of Shanley, is just a little bit greater than the PCR of the uh, tangent modulus theory. But we cannot use PS since the more critical value will be the smaller value, and therefore the accepted theory that is now used is the basic tangent modulus concept. So although double Angular is correct in his equation, it so happened that the value of PS, considering residual stresses and inelastic behavior, match very well on the work of Angular on the assumption of the tangent modulus concept. And this is the one that is now being used by the AISC as the basis for the strength of your column. So take note that for practical purposes, the increase in the capacity of PCR to PS is neglected, and hence the tangent modulus is the one that prevails. And this is the PS, or the Shanley load, is now uh, reduced to a PCR load of Angular in this context, which will give you some modifications later on the AISC because of the effect of residual stresses. And what are residual stresses? So residual stresses are simply the effect of uh, the following factors. It explains why the sigma epsilon curve becomes nonlinear beyond the proportional limit. So the residual stress is the cause of that. Stresses that remains in a member after it has been formed into a finished product and results from plastic deformation. So again, residual stresses are the cause. And several causes of residual stresses due to manufacturing are these ones identified below. So uneven cooling, which occurs after hot rolling of structural shapes, cold bending or cumbering during fabrication, punching of holes and cutting operations during fabrication, welding, and a lot more. No? Which simply states that the process of producing steel, we cannot avoid the the material to undergo a an increase or undergo this residual stress increase because of the processes involved has something to do with it. Okay, it has something to do with temperature, uh, temperature introduced, no, in the member. It has something to do with the pressure introduced also in the member, and it has something to do with the initial stresses brought about by punching, cutting, welding, etc. Okay, so we cannot avoid such residual stresses to happen or to be in what word can I place, to be induced, okay, in the material prior, and this is prior to the application of the load. Okay, so how to measure and how to consider the residual stress uh, uh, behavior, no, of the material will be the problem of the uh, material engineering, and all we have to do is to come up with a way of approximating such residual stresses for us to be able to account on it when we examine the behavior of the member during the application of the load. So for this, the Structural Stability Research Council, which is the basis for the AISC formula, gives us this parabolic equation as a starting point for us to be able to understand what uh, are the needed, okay, equations for us to be able to measure the strength of the column. And the parabolic equation of the SSRC is the basis for the ASD. Okay, so it is called the parabolic equation because this equation here is actually a parabola, and this equation here is simply the Euler equation. So this is simply an Euler equation in disguise. Okay, so it is an Euler equation in another form. Okay, so I will explain to you what is lambda c squared here. Okay, for ASD, your limit, remember the limit that I told you a while ago about the c sub c. This is the limiting value of the KL over R involved. Okay, so remember that when we are designing a steel member on compression, what we are interested on always the KL over R ratio. And this KL over R ratio is compared to the limit of C sub C given by the square root of 2 pi squared E all over Fy. And this 2 pi squared E over Fy was derived from this parabolic equation of the AISC coming from the SSRC council. Okay? So, what is lambda C? Lambda C is just a dimensionless factor. Okay, so this is which gives us okay. Remember what we note on the previous discussion, that if this is your okay. Okay, so this is now your parabolic curve, which is the basis for your ASD. And the limit of the parabolic curve with that of the Euler curve will be lambda sub c, okay, in general. And lambda sub c, as I've told you, is actually square root of 2 or approximately 1.5. So all of the values of your f, okay, so this is your f versus lambda sub c or lambda will fall on this curve, eventually are on the inelastic mode of failure, and those will fall beyond this curve and touches the Euler curve will be on the elastic mode of failure. Okay, so whether it's ASD or LRFD, it's just the same. The only problem is what is lambda sub c in LRFD and what is lambda sub c in ASD. Okay, in ASD, lambda sub c is more popularly known as the C sub c, which has something to do with the KL over R ratio. Here, this is dimensionless, and here, this is not dimensionless. This is a slenderness ratio. Okay, so dimensionless, and this is a slenderness ratio. Also dimensionless because this is in terms of, but it is more of a property on the ASD, and this is more of a property in LRFD. Okay? Okay. So if we equate now the lambda sub c, which is square root of 2, with that of your KL over R square root of Fy over pi squared E, what happens? You get now the limiting value for your C sub c. Okay? How did this happen? No? So this ratio here, so this expression rather, okay, this expression here is simply the value of your Fy all over FCR. Okay? What is FCR? FCR is simply equal to pi squared E over KL over R squared. Okay, so I can put this below. Okay, so this is simply pi squared E all over KL over R squared. And this is Fy. So the ratio of Fy over FCR now becomes your basis for your lambda sub c. So if I take the square root here, I have to square that. Okay? If I take the square root of this, I have to have a square root of this. That's why this now will give you a value of your limit KL over R, which is equivalent to CC, which is pi squared E all over Fy. Okay, so the formula now for CC is 2 pi squared E all over Fy. Okay, so how come there's a 2 here? Now, the 2 here came from the square root of 2, which is lambda sub c. And if you take the square of that, that is actually equal to 2 here. If you want to take out the squared sign there, this becomes squared, and this becomes without the squared sign. So this is what happened. If you will jump the formula on ASD and LRFD, this is the relationship between these parameters. Okay, so the next thing here that I'd like you to by the way, before I proceed with this, I can now make my formula about lambda sub c equivalent, okay, equivalent to Fy over FCR, okay, Fy over FCR, such that my formula now for lambdas of c will simply be equal to this formula here. So if I want to get the lambdas of c limit, I use this formula. If I want to get the c sub c limit, I use this formula. So let me now show you how to plot it in MathCAD 4 or MathCAD 15 using a MathCAD solution. So this is just MathCAD a keyword I define, okay, such that your equation for, sorry, your graph for the equation on the function c sub c, okay, is as a function of the lambda sub c limit here is in this form. Okay, so how do we interpret this? What is this vertical? Okay, what is this vertical axis here? So simply, this is your FCR over Fy. Okay, which is what? Which is the lambda c. Okay, against the c sub c limit defined, no, on this axis. And what is your limit for c sub c? The limit for c sub c, if Fy is 36 ksi, I think is 126.1. Okay, so if I use this now, this value of 126.1 here, I can get my value for FCR over Fy to become at almost 0.50 or 0.50. Okay, so how do I solve for FCR now? I simply equate 0.50 times Fy, that's my FCR. Okay, so that's how this graph works, no? Relating your lambda sub c with that of your your c sub c limit. Okay, so the basis for slenderness limit now is given again. This is the limit for LRFD. This is the limit for c sub c, ASD. And in order for you to be able to capture the FCR, you have to use, of course, the formula both on the SSRC. So for ASD is SSRC plus Euler, and for lambda sub c LRFD you will be getting the inelastic formula plus the elastic formula. Okay, so these formulas are not yet derived, so I will be deriving this formula for LRFD on the next video. Thank you very much.